Welcome everyone to my talk, Atypical Spectra Screening, Applications for Monitoring Infrared Instruments and Model Predictions. In the next few minutes, I will show you how we can routinely screen milk spectra for systematic abnormalities caused by temporary measurement instabilities. I will also show you how this can give valuable information about the validity of model predictions and the maintenance status of our instruments. Fourier transform mid-infrared spectrometry is the method of choice for determining the composition and quality of liquid milk products. Simply said, this works by using an infrared instrument to measure the milk's absorption spectrum. Mathematical prediction models can then use that spectrum and calculate or estimate from it the concentration of fat, protein, lactose, and many other parameters. How accurate our estimates for these parameters eventually are depends on many things. It depends on how good the prediction model is, that is, how robust it is. It depends on how suitable the model is for the type of milk. And of course, it depends on the quality of the spectra, because ultimately that is what our prediction models use to calculate an estimate. At this point, we should not forget that each obtained milk spectrum is the result of a measurement process. And each measurement process takes place under certain conditions and by using a measurement instrument that is subject to wearing and instabilities. Any change in the measurement process can therefore result in systematic deviations in the spectrum. If these deviations occur in spectral regions that contain chemically relevant information about the milk, our prediction models may produce wrong or invalid results. Moreover, if the instrument produces spectra with systematic noise, it may indicate that something doesn't work properly with our instrument and maintenance might be required. You could now say, why should we care? This is exactly why we use control milk samples, where the concentration of fat, protein, lactose, and many other parameters are analyzed with a chemical reference method. If the model predictions for the control milk sample then differ from the chemical reference, a slope-intercept correction can be performed, and our predictions are accurate again. This works well for chemicals that are present in your control milk samples. But what we see is that there is a growing interest in quantities that are not directly present in the milk. This can range from using information in the milk to predict pasture intake, methane emissions, or NAFAs or beta-hydroxybutyrate in the blood, and so forth. So how do we monitor the quality of these predictions? There often simply is no reference analysis that can be applied to the milk sample. What we therefore need is a more general approach when it comes to quality control of our data. One way to achieve this is to monitor whether the conditions under which we obtain our spectra are stable. And the good thing is, we can do this very easily with the tools and the data that we already have. In the next few minutes, I'm going to show you how models originally developed to screen for adulterated milk can also be used to monitor individual infrared instruments. This can provide valuable information about the validity of the predictions and even the maintenance status of our instruments. In essence, this approach is based on establishing a milk fingerprint that is unique to a particular infrared instrument while still containing the normal variation found in the milk. Such a fingerprint can be developed using a representative collection of milk spectra, all obtained from a single instrument. Once a fingerprint is established, we can use a new milk spectrum measured on the same instrument and compare it to the fingerprint and compute a so-called anomaly score for that spectrum. This anomaly score summarizes how different the milk spectrum is from the fingerprint. Of course, the higher the anomaly score, the more spectrum deviates from the fingerprint. The question then is, what do we do with these scores? So we are not so much interested in the anomaly score of an individual milk spectrum. Instead, we are interested in systematic changes that occur within a particular time window. What you see here is an example of the anomaly scores of all milk spectra measured on a single instrument during one day in our milk payment laboratory. We do see some random fluctuations and extreme values here and over there, but on average, the anomaly score nicely fluctuates around the zero line. And this is exactly what we expect to see if everything is all right. This here is a case where it gets really interesting. This is from another instrument and another day in our laboratory. The anomaly scores here show a clear upwards trend, and this is not due to measuring increasingly abnormal milk samples. Instead, this here results from instabilities in the instrument, and this results in systematic changes in the measured spectra. And let me show you what I mean by systematic changes in the spectra. In this figure, you can see on the x-axis the wave numbers of the middle infrared region. The gray shaded areas here represent also the regions that partly our prediction models may use to generate predictions about the chemical composition of the milk. On the y-axis, you can see the spectral residuals. In other words, by how much the spectrum deviates on a particular region in the infrared spectrum. Remember, as long as we only see small and random fluctuations, everything is all right. Everything that manifests as a clear and persistent pattern is most likely due to instrument instabilities. Let me show you what happens when we look at each individual milk spectrum measured during that day on this instrument. At the beginning of the day, we already see how the anomaly scores start to drift upwards. And if you pay close attention to the spectral residuals in these regions here, you see a systematic increase in these regions. And this is not just random noise. This is systematic deviations that result from measurement instabilities. Although we don't really know what has caused these instabilities, we do know that they affected predictions of urea in this case. The orange line here shows a smoothed average of urea predictions over the day. And you can clearly see, as the anomaly scores start to drift upwards, we see a decreasing trend for our urea predictions. And at the same time, where the anomaly scores tend to go back to normal suddenly, admittedly, we also see the same thing happening with our urea predictions. Here's another example from another instrument on another day. This time, the anomaly scores did not change gradually as in the example before, but abruptly, and they affected the predictions of free fatty acids in the milk this time, here depicted in the red smoothed curve. Again, the bias in the predictions coincides with a systematic change in the anomaly scores over here and there. By the way, all our instruments are standardized on a monthly basis, and all predictions are obtained from commercial models installed on these instruments. Moreover, from checking the control milk samples, we know that the prediction biases that we see here in these lines are actually due to instrument instabilities. And this shows that such instabilities have a potential to affect model predictions. And these are certainly not the only events we identified. With this knowledge in mind, can we find a way to automatically detect events like these and in real time? The short answer is yes, we can. We applied a Bayesian online change point algorithm, and we were able to accurately identify events like these in real time. The black vertical lines you can see here, there, and over there represent the moment in time that our change point algorithms were able to detect that something has changed in the anomaly scores. And if you look closely, you can see that it works with a very, very short delay. And in fact, we found that in our cases at least, 24 spectra were often sufficient to identify most of such events. But we can do much more than that. So far, we only focused on instabilities on the scale of minutes to hours. However, we can follow individual instruments also on the scale of weeks, months, and even years. What you see here are the 4 instruments in our milk payment laboratory with the anomaly scores calculated for all milk spectra obtained between 2018 and 2020. We also applied the change point algorithms mentioned earlier, and the red spikes that you see here reflect the confidence with which a change point has been detected at this moment in time. So the first thing that we notice is a steady increase in the anomaly scores across all 4 instruments. But we also occasionally see sudden jumps in the anomaly scores. This is particularly evident when looking at instrument D from February 2020 onwards. At around the same time, interestingly, our colleagues in the lab noticed increased problems with this instrument, mainly in the reliability of the predictions. Unfortunately, for most of the instabilities that we discovered, we do not really know why they occurred and what they reflect. We could not retrospectively relate them to maintenance work or documented malfunctions. What we can do, however, is trying to find out whether it is always the same type of instability or a different one every time. For this, we identified 38 events with instrument instabilities over a period of 3 years and across all our 4 instruments. With a bit of math and magic, we identified several clusters in the spectral residuals. The first thing you see is that even though the instruments are actually all the same model from the same manufacturer, they are clearly separated from each other. This is also exactly why it is important to develop separate fingerprints for each individual infrared instrument. The second thing you will notice is that some of the clusters are quite small. These clusters only contain spectra from a single event. Other clusters, however, mainly these ones, contain spectra from multiple events or instabilities. And this suggests that the same type of instability can reappear over time. For future studies, it could be interesting to investigate whether these clusters can actually be linked to a particular event or a malfunction in the instrument. As we are coming to an end of the talk, I would like to wrap up by reiterating that our approach can be used as a quality control tool for monitoring the validity of our model predictions and the status of our instruments. Because we focus on the raw spectra underlying all predictions, our approach is more general and more sensitive than using control milk samples and slope-intercept corrections alone. Our approach does not rely on expensive chemical reference analysis or any control mix samples at all. Instead, it is based on the spectra that we routinely obtain in our laboratory, and it can be developed with the tools that are already existing. In other words, it can be developed and used by every laboratory. Thank you very much for listening to me.